Hey guys, what's up? Eddie Alho here with KissAnalog.com. So today we are going to jump into the second part of our power supply design. We're going to go over a block diagram of the major components of the power supply and how to select those parts. The bulk capacitor, the bridge rectifier, the power transformer, and the fuse. And we're going to talk about how the selection of one affects the selection of the next and the trade-offs and so that we can choose the right parts. So let's jump in. Okay, so this is our simplified block diagram using the KISS method, and this is for the power supply design for the audio amplifier, and this pretty much breaks it down to input power coming into our circuit protection, then into our transformer, our step down transformer, because we're stepping down the voltage. In the last video we saw that it was we needed about 32 volts, maybe 33 volts for the amplifier circuit to work correctly. We're going to talk about the voltage we're going to need because of the power supply. But then, so we have some circuit protection, transformer, and the AC/DC block. That AC/DC is a bridge rectifier with the bulk capacitor. So I've kind of drawn it here in pencil, and this is our AC voltage source, our fuse, and our transformer, primary winding, and our two secondary windings. The secondary windings are tapped off in the middle to ground. You can kind of think these transformer windings as just in series, so we have a plus and a minus voltage, but the center tap, kind of like a voltage divider, is the 0 voltage point, which is ground. So we'll have a plus minus voltage come off transformer. It'll come into this bridge rectifier, which, if you want to draw one of these, just draw a square kind of on its corner and then draw on the diodes, and you can see the arrows point in the direction of the current flow. So this is our plus voltage out, so the arrows both point to this one. And this is our minus, so the arrows point away from it. So plus coming off the bridge rectifier here, minus coming off here. The AC comes in here. It has when this side's positive, it can go this way. When this side's negative, it'll go that way. Same with this one. When it's positive, it goes this way. When it's minus, it goes this way. So these steering diodes just tell the voltage where to go. I made a video to talk about diodes and bridge rectifiers and power supplies and how that works, and how the capacitor and the transformer all play a part into this. And so you can watch that video on how bridge rectifiers work in a power supply to see that. So off the output of this plus minus voltage, we put two capacitors, and the center point of those, kind of like another voltage divider, the center points to 0 voltage point, which is referenced to here. And we have a minus capacitor, a capacitor, that gives us the minus voltage, and a capacitor that gives us plus voltage. So again, these capacitors are in series. You can think of it that way across the full voltage. So I've kind of drawn a waveform here. This is our AC waveform. That's what we see on this side, and that's what we see on this side. But then once it goes through this rectifier over here, we see this pulsating DC waveform. So I kind of got a little dashed line. I hope you can see that. It's so we got this AC waveform, and instead of going negative, it turns into a positive side. These diodes steer it, so we have positive. So this time, this time for a cycle is equal to about 16.7 milliseconds, and that's because we have 60 hertz. Frequency is equal to that, and of course this time, is so let me see. The relationship is T equals F. Oh shoot. I'm glad I got a pencil here. Trying to think ahead. Anyway, T equals 1 over F. So 1 over the frequency is your time. 1 over 60 hertz is 16.7. So half a waveform is roughly 8.3 milliseconds. So that's the time it takes here. So that's the time it takes between a positive pulse and another positive pulse. So this capacitor over here is going to give us a cleaner ripple. So the voltage is going to charge up, drop to some point, and then charge up and drop to some point, charge up, and repeat over and over. So we get 2 charge cycles. And what these little pointy things are the current that is going through these diodes as it charges these caps. So I'm just showing the positive cap at this point. Same thing's happening on the negative side for this capacitor, but on the positive side for this capacitor, each one of these pulses that get steered up here gives a charge cycle for that capacitor. And it's narrow because it's only on, so when that voltage discharges and the next cycle comes up, right at that point it turns on to charge the capacitor. So just during this time here, you get a charge cycle, so you get a big peak of current, then it turns off. So the voltage is this nice, it's becoming flatter and flatter, and you get constant voltage, but current gets narrower and narrower, and so you get these really high current pulses. And again, I talked about that in the other video in more detail. Show a simulation showing the current voltage moving around, makes it much easier to see what's going on. Okay, now let's go and see, when you select a capacitor, for instance, it affects these other parts. Like I just say, the larger the capacitors, the higher peak currents you get going through these diodes. So this capacitor selection affects these voltage, or the current in these diodes, and also this transformer. So the transformer steps down the voltage, also gives us isolation from the primary side of the circuit to the secondary side of the circuit. Current here is traveling here in a circle from the voltage to the fuse to the transformer and back, but it doesn't, this current here does not cycle here. It's magnetically coupled, so we have isolation, magnetic isolation, and so the current here comes off of this transformer and cycles through these diodes through here, and like I say, you know, it's this circle current here is roughly this. It's a little more complex because it, you know, one side of the waveform goes one way around, and the other cycle comes, when it's positive down here, goes this way through the capacitors and around and then back up to the top. So it always has a complete circle, and that's why you need 4 diodes, so that you can break that path. When the voltage switches over, you break it and you steer it a different direction. When it switches back this way, you break it and steer it the other direction, so you get these positive pulses up here and the opposite on this side. So okay, so let's go and see how you actually use some math to calculate the value of these. It's got, you know, a simplified equation. Let's go look at that. Okay, so this is our capacitor sizing. This is kind of how we began. We'll start with this to kind of show how it's done. This is for this power supply design for the audio amplifier. Now this is our 60 hertz coming in, our power, and this voltage is what we have to decide what we're going to do, what we're going to, what size we're going to make it to. You know, that's going to come off the transformer, but it's 60 hertz is equal to 16.7 milliseconds in time from here to here for one cycle. Sorry about the funny looking waveform, it's not the best drawing. Now from peak to peak, now if, you know, once we go through our bridge rectifier off our transformer, then we'll take this negative going peak and we'll, let's see if I can draw this, we'll bring it up here, and it'll be another positive pulse. So we'll get 2 charge cycles and 1 60 hertz cycle. So the time between charge cycles is 8.3 milliseconds. Okay, now we have some math down here, an equation, but before we go into that, let's just jump into it right now. The equation for a capacitor is I equals C, change of voltage divided by change of time. So we know what the change of current, or I'm sorry, we know what the current is. It's 2.5 amps RMS for the 50 watt condition, and the change in time from cycle to, from one charge cycle to the next charge cycle is 8.3 milliseconds. Now this change of voltage, that's the thing we have to decide, is how much ripple we're going to allow on our power supply. Now for the music, we said it's going to peak at 28.28 volts, and we're going to give 4 volts of headroom for the audio amplifier, so that's 32.28. And for the power supply, we're going to need some voltage. So let's say we give ourselves 4 volts like the audio amplifier did. Now this is likely to change. Basically, the transformer selection might force us to have a higher or even lower voltage, but let's just see what we do with 4 volts. So for this equation, we know we know 3 of these things. We just don't know what our capacitor is. So we solve this equation to put our capacitor on one side. To do that, we just cross multiply. We get rid of the time down here by multiplying this side of the equation by time. We multiply this side by time. It doesn't change the equation. So to get rid of the voltage, we divide this side by voltage, and we divide this side by voltage. As long as we do it both sides, it's fine. So we end up with this. Those two things disappear, and we get the change of time up here and change of voltage here. So it's capacitance is equal to current times change of time divided by change of voltage, which translates to these numbers. Sticking these numbers into the equation, and it comes out to 5.25 millifarads. That's 5,250 microfarads. So that's the minimum size of cap we want if we're going to allow 4 volt ripple. So that's a consideration, and and we're going to look at the other parts of the design, and like I say, we'll iterate. And I'm also going to show how we would choose a capacitor based on maybe a 2 ohm load instead of this 50 watts is based on 8 ohms to give us the 2.5 amps. So we'll see what the large sizes of this cap might want to be, and then we can kind of see what our range of capacitance will be. Okay, so for now, based on this, I would come up here and I would say, here's our 20.28 volt peak of our music. Here's a 4 volts headroom for the amplifier, and then another 4 volts above that would be about 36.28 volts would be our plus rail for our power supply based on this. Okay, now let's look at another case for capacitor size based on a different ohm impedance. Alright, so I'm calling this a worst case scenario. I'm saying 20 hertz, lowest frequency. It's the slowest frequency in our audio band, the 20 hertz to 20 kilohertz. So I'm taking the slowest one and saying that we get this big old slow frequency at our maximum 28 volt peak. Okay, that's our music. I put current because that, but here let me show a 28.28 volt peak. Okay, and that translates into 2 ohms as 14.14 amps peak. So we get this big pulse of current, and now the good thing is even though I said it's worst case, it's because I would think that it would be the lower frequency where we might get the lower ohms, and so the time for a cycle at 20 hertz is 50 milliseconds. Okay, the good part about that is is our that's much slower than our 60 hertz power coming in. So our transformer, our AC power comes to our transformer, charges the capacitors, and we get 3 charge cycles, because 20 hertz is 3 times slower than 60 hertz. So we get 3 charge cycles on our 60 hertz power coming in. So we said before we're going to let the voltage drop 4 volts peak. So now we can say 3 times 4 volts is our change of voltage in our equation. So we'll have 12 volts to work with. It won't actually drop 12 volts. It's going to drop 4 volts, but then it's going to get charge pump, and then it's going to drop 4 volts, get charge pump. So it'll happen 3 times in this same time period. So back to our equation, I equals C, change voltage divided by change time. Changing the equation around, we put the numbers in, 14.14 amps times 25 milliseconds, because what we're going to do is we're going to calculate half a cycle. And so that number comes out to 29 millifarads, 29.46 millifarads. It's 29,000 microfarads. So that is 29,460 microfarads. That's a big capacitor. Okay, so that's our worst case scenario as far as capacitor size goes. And so just wanted to show that. And the 2 ohms, I looked at some speakers, and we'll talk about speakers too. I'm going to actually do a little sidebar on that, and I'll show a little supporting video about the ohms and what you can really, what I think you can expect. But so there we go. We went from roughly 5 millifarads to 29 millifarads. Okay, so we know we need a capacitor somewhere in the range of 5,000 microfarads to 29,000 microfarads, and we have a maximum of 36.28 volts on a rail that we need or we want. We might not get that depending on the transformer, because we gave ourselves 4 volts of margin above what the amplifier needs, which is 32 volts. So over here I did some math. What I did is I took the 36.28 volts, I added 5% for the line voltage, the input voltage, the 120 volts coming in, plus minus 5%. If it goes up 5%, it's gonna increase our voltage on our transformer 5%. So we want to make sure that we have that voltage derating. Well, and then also we have 10% for our transformer regulation. At light load, it'll float up 10 volts or 10%. So that the 5% came out to 1.8 volt adder. 10% gives 3 volt adder, and that comes up to 41.9. And then we want to derate our capacitors 70%. That's kind of a typical standard in the industry, so for aluminum electrolytics, and that would take us right to about 60 volt rating on a capacitor. So there just so happens that we'll find 63 volt is a standard rating. So sounds like a capacitor in this range at 63 volts is what we want. Okay, so let's jump into the capacitors, and I think we're going to go to Mauser.com for that. So let's look at that. Okay, so at Mauser.com, what I looked at was 63 volt caps, and somewhere around this range we're looking at, what I found was a bunch of 6800 microfarad caps, 63 volts, and some are snap ends and some are screw ends. They're usually the larger ones. So look at that, $21 for screw end. But let's just go over here and look at something. 10,000 hours and 11.5 amp rating. It's pretty darn good. Come up to this one, it's 4.5 amps at 3,000. And it's much, well, let's look at the size, 25 by 50, and this one was 36 by 73. So same ratings here, but much different as far as the current. And this one's $4. Okay, but and this is a Cornell Doobler, but then I see this one at $3.83, and it's a Cornell Doobler as well, and it looks like it has very similar ratings at 59 milliohms of ripple. So now the thing is, it's larger, 30 by 40. This is 25 by 50, so you're paying for that smaller size. So we come over here, and they're again same kind of ratings. So I'm not concerned about this one being 5 millimeters larger in diameter. So, and they have 987 in stock. So I think that looks like a good one. There's the part number, and it's going to look something like that. It's probably an actual picture. So okay, that looks like the one. Now, by the way, I think I'm going to put two of these in parallel. Even though this one is within our range and it has 4.5 amps, I want to be able to go be a little higher peak currents than that. And so I think I'm going to do two of these in parallel for the plus and two in parallel for the minus. Okay, I think I'll buy this one. Alright guys, what do you think? Thumbs up?